All right, good morning. Hope you're doing well. Happy Wednesday. Happy next to last day of Chem 221 lecture. What we're going to do today is start a review for the lecture exam next week. As a quick reminder, next week, what's happening is Monday morning by 8 a.m., you will get a link, an email link to the lab time, and you should print that out and start working on it. And the lab final will be due Wednesday at the time of your lecture final. And for you in section 01, the lecture final will be in this room, 8:45 in the morning. The lecture final will go about 2 hours. Turn in the final exam prep as well as the lab final. And by 10:45, get done with Chem 220. Now, questions? Anything?
No lecture Monday?
No lectures Monday, that's right. There are no lectures and no labs next week at all and stuff, yeah.
Just the 2-hour lecture on Wednesday until we get.
That's right, that's right. It'll be in this room, you can have a page of notes Donovan was asking about, absolutely. Turn it in with the lecture final. You can have scratch paper next to you to write stuff on, absolutely. Periodic tables, cool. Bring a calculator, definitely. If you have any late work, get it to me by Friday. That would be super cool. Anything? I'm probably missing something. So, but,
This Friday.
this Friday, the late work is due. That's right. Yeah. One of the things that some of you have seen and heard about, we've had 2 power flickers this morning already. One right before I started turning things on. So if it happens, we'll just go with the flow and stuff like that. I heard there was some kind of electrical work being done outside, or I don't know. Gotta love Mother Nature. Anyway, Prophet back on. Questions? Let's do it. I'm going to focus in this review on chapter 6 stuff because that's the newest stuff, all right? And this will help go along with the problems that we did yesterday too. But anyway, so I'm going to focus on that. The actual lecture final does have stuff from other chapters. There's a little bit more over the chapter 6 material than the other stuff, but it's all going to be there. So this is a question going back to the Bohr model for the atom. And we have the first 5 energy levels. And the question is, how many emission lines are possible? So see if you can figure out here how many emission lines are possible for the first 5 quantum levels of hydrogen, the first 5 energy levels. We'll talk about this in just a minute. If you have an iClicker, of course, you can participate, and if you don't, we'll just write it down and talk about what's going on here. Right, so before Bohr and his work, people understood that there were like these sharp line spectra in hydrogen, which you all saw now on Monday. And they were fascinated by it because they're kind of cool, and right, you don't think that a blue-red or blue-purple bulb would have all these individual colors within it. So it was really interesting to them. And Balmer was the person that studied the visible lines, and I think this guy named Paschen was the infrared guy. But anyway, they didn't understand how they correlated it all. So Bohr came in with this theory kind of at random, where the nucleus, which I've just put as a positive sign right there, is separated then by electrons that can jump between different levels. And he talked about, and we talked about too, how the energy levels have a -1 over n squared dependence, and I'll talk about why that's important here in a little bit. But in the Bohr model, electrons start at the lowest level, and they gain energy to go to a higher level. And because this is an energy axis, that makes this an endothermic transition. The electrons don't just naturally jump up there, you have to add energy to them. So if the electron goes from a lower end to a higher end, this is what they call an absorbance line. And in biology and chemistry and lots of other sciences, absorption spectroscopy is huge, all right? And you'll definitely run across this, I would imagine, in the future. But what we're talking about in Chapter 6, more than absorbance, and in this problem specifically, is the opposite process. So if you have an electron at a higher end, maybe it gets homesick and it wants to go back down to where it came from, all right? This is the opposite direction. And like we've seen in chemistry, if one direction's endothermic, the other direction is almost always exothermic. So exothermic lines mean higher end to lower end, and you always get energy off. And these are the emission lines. So on Monday, when you saw the red line, green, blue line, maybe a purple line or two, those lines were higher end electrons going down to lower end electrons. You can actually see them, and that's what our light bulbs use right now to give us light too, which is kind of cool. So what I've just drawn here, the 5 to 1, is one of these emission lines, all right? That's going to be the biggest energy. It's the biggest arrow between the two. All the other ones will be smaller. But there's really no reason why we had to go 5-1. That electron could have also gone 5-2, 5-3, and 5-4. So you can also put up here the 5-1, besides the 5-1, you could put the 5-2, 5-3, pretty lucky 3, and 5-4 transitions, and those are all legit. So those represent 4 transitions in these first levels. But as you can probably see, I've been starting on n=5. You could also start on 4. So you could have 4-3, 4-2, 4-1. This is something they use sometimes in higher types of chemistry to talk about these transitions. We don't have to worry about that, but that's what I'm talking about. What is important here is that we have 1, 2, 3, 4, 5, 6, 7 transitions just from these. But of course, you should also do 3 to 2, 3 to 1, and 2 to 1. So 3 to 2, 3 to 1, and 2 to 1. So if you count this up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's going to be 10 lines possible. Right on. I'll have you present at the end. Is that correct? So, yeah, good to see you, man. So, Jose was gone last week for good reasons. Good to have you here. So, all right. So anyway, back to your regular scheduled programming. 4 lines from the n=5 level, 3 from the 4, 2 from the 3, and 1 from the 2 for a total of 10 emission lines possible. So, cool. Now, in the hydrogen spectrum lab that we saw on Monday, all of those lines were lines that ended up at n=2. So the thing that had them in common, besides them being visible, was that you had a 3 to 2, 3 to 4 to 2, 5 to 2, and a 6 to 2 transition. And some of them were easier to see than others. So, yeah.
So let me try my best to get this straight. So the first line, you know, it's the ground, where it always is. It can't emit from the first line, right?
So let's make sure we're using the right terminology here. Are emission lines higher end to lower end, or lower end to higher end? How about Ben? Higher end to lower end, or lower end to higher emission? Higher. Yeah, higher. So let's talk about it correctly, Ben. It would be like 2 to 1, not 1 to 2. Okay, because 1 to 2 would be endothermic, a whole different energy sign, which you know is important in my world, and you wouldn't see him quite as easily. So yeah. So now ask your question.
How come it's 10 emission lines if it's showing 4?
So 5 to.
Oh, I see it now. I see it.
Good. The light just came on. Good. That's perfect. I'm glad you asked. Good.
Sorry
Good.
about that.
No. This is what this time is for. So don't you worry at all. Good. Other questions? Okay. Now, because these are all energy lines, energy transitions, you can start doing things about highest frequency, highest wavelength, lowest wavelength. So this question says, photons of the highest frequency will be emitted in which of these transitions? So really what I want you to do here is I want you to think about how highest frequency relates to all of these lines right here. So think about that, what frequency is relative to these lines. we'll talk about it in just a second. Okay. So when Ben asked earlier, I wanted to make sure it was clear that we were all talking about emission. Emission is going from higher end to lower end, and these are emission ones too. But why it's important is that there's a huge difference in chemistry between something that's endothermic, that can add energy in, to something that's exothermic, that gives off energy. And so all of these lines right here represent energy transitions. They're all exothermic. They'd all give you negative joules, kilojoules, whatever. And because the y-axis is an energy axis, then you can tell which is the biggest energy based on which one is the biggest arrow. So of all of these transitions here, which one is going to be the highest energy transition?
5 to 1.
5 to 1, well done, that's right. It's the biggest arrow, the biggest drop, if you will, and stuff. You'll get the most energy off upon doing that. So we can all say that the highest energy is 5 to 1, but we're after frequency here. So as energy goes up, does frequency go up or does frequency go down?
Up.
Up, that's right. So highest frequency will be highest energy. It's gonna be the 5 to 1 transition, right? Energy and frequency are proportional. And once you see how this is an energy axis, the largest arrow will give you the most energy, and most energy means highest frequency. Any questions on that? What we're using here is E equals H nu, all right? Where the nu is the frequency symbol and E is the energy. And H is Planck's constant, just a number. So as frequency goes up, the energy goes up, or vice versa, all right? Or as energy goes down, frequency goes down, et cetera, et cetera. All right. Now, this question is also very similar, but now we want the longest wavelength, all right? So same 5 lines, same emission kind of question, but which one is going to give you the longest wavelength?
2 to 1.
Which one?
2 to 1.
Because there's a 1 over n squared dependence, it's like 1 over 1, 1 over 2 squared, 1 4, 1 9, 1 16, 125. Aha, good. I just saw the light go on. So it's not going to be 2 to 1 because this is actually 1 to 1/4 would be 3/4. What do you think? Yeah.
So the closer to the nucleus it is, the higher frequency.
So frequency depends on energy, and you need to look at the line spin to figure that out. So it's not closer to the nucleus, it's closer, it's the biggest line, all right? So the biggest line is 5 to 1, that's why that was highest energy, highest frequency, all right?
Isn't it like 5 to 4 because it's like really close to it?
5 to 4, well done. These lines get closer to each other as you get higher and higher, all right? And the 5 to 4 transition is smaller than the 2 to 1. This picture kind of does it. I tried to do it a little bit better. If you're a math person, it's a 1 over n squared, but you don't have to worry about that. Just realize that they get tighter and tighter and tighter as they get closer and closer. The 2 lines in the visible spectrum, those 2 purple ones you saw on Monday, if you had that, those are both about the same color because they're both pretty close in their transitions to each other. So 5 to 4 would be the smallest energy, and energy, if you keep going here, also equals hc over lambda, and lambda is the wavelength. So if you want the longest, the biggest wavelength, biggest denominator, you want the smallest energy. That will be the 5 to 4, the smallest arrow.
Find the highest ratio.
You bet, that's right. Yep. Yeah,
And C is the speed of light.
that's right. C is the speed of light, another constant. You bet. H still is Planck's constant. Good, good, good. Other questions? Now, here's a question to make you think a little bit more about all this stuff too, all right? We've got two transitions, all right? We've got an n equals 4 to 2 and an n equals 3 to 2. And so it's questioning here that what color will the 3 to 2 transition be? So in this case, the 4 to 2, all right, is a green light transition. So the question is then here, will the 3 to 2 transition be red or blue? It won't be ultramagnetic, that's the name of a bad rap band from the 80s, don't worry about that. However, I do want you to think about all the things we've just talked about then, and think about what that's gonna be. Now, what it's saying is that 4 to 2, this gap, all right, is gonna be green. So 3 to 2, I would start thinking about energy, how it applies, and then see if you can use that energy relative to 4 to 2 to think if it's gonna be red or blue. We'll talk about this in just a second. Just wrote on the board up there, Roy G. Biv. Does anybody know what that's about?
It's the rainbow.
The rainbow is an
Electromagnetic spectrum thingy, or the colors.
Yeah, the colors of the visible spectrum. That's right. Well done. Roy G. Biv is the order. So red is red, RR, orange, yellow, green, blue, indigo, violet. And if you've done stuff like that, that's cool. Now, this 4 to 2 transition is green, right in the middle, all right? So if you knew if, like, say, red was lower energy or higher, blue was higher and lower, then you could figure out what's going on based on what we talked about. So does anybody know, do you think red is lower energy or higher energy than green?
No.
Lower, nice job. So red is lower energy, blue and all these are higher energy. And again, the green is going to be 4 to 2, all right? And going back to what Ben and I were talking about, 4 to 2 would be this arrow right here. So relative to 4 to 2, is 3 to 2 going to be higher energy or lower energy? Lower energy, all right? So if it's lower energy than green, it can't be blue because that would be higher energy. This one's going to be red, all right? So if you use all these pieces and stuff and put it together, it's kind of cool. You don't necessarily need to know Roy G. Biv, it can be helpful. Infrared is lower energy than visible light. So that's another way to realize that, yeah, red is probably lower. And ultraviolet, all right, which is V, would be higher energy, like skin. So, but if you know those kind of things, of course, it's helpful. Any questions? Okay. Now, another thing that's really important in this section is being able to go from, say, wavelengths and nanometers all the way up to kilojoules per mole. So this is a question, kind of like what we saw yesterday, or Monday, excuse me, in the lab, here's an energy 182.3 kilojoules per mole. What's gonna be the wavelength in nanometers? Work on this a little bit. I'll put a couple of hints up here in case you get stuck. And if you happen to remember from the lab, there's a fast way to do this problem too. But we'll talk about the long way and then the shorter way too. Okay, so if you can do this kind of problem, all the math in this section will fall for you, but I know it's a little weird at first, so I want to spend a little bit of time going over again how this works. It's very common in this section to have a wavelength in nanometers that you need to turn into kilojoules per mole, or the reverse, which is what we're doing in this problem. We're starting with a kilojoule per mole and going to nanometers. So along the way, kilojoules per mole, you first need to turn the energy in kilojoules per mole into what's essentially joules per photon. And these will be really small numbers relative to these kind of things here. Now to do that, a mole of anything is 6.022 times 10 to the 23rd. In this case, it's photons per mole, so that's what it is. So take that and divide by Avogadro's. And then you're also going to multiply by 1,000, not 100, sorry, 1,000 joules per kilojoule. You good? Oh, yeah.
Yours. Sorry.
There's one in the back there wanting me to put it back there. So. 1,000 joules per kilojoule. All right, so the kilojoules times 1,000 will give you joules. And that'll give you a really small number, which will be the joules per photon. That's the energy of individual photons. And once you have that, that's when you can go E equals h nu. Now really, you could have went straight to wavelength on this problem, but I'm going to show you all the details. So if you wanted the frequency, energy equals h nu, you would divide the small energy by Planck's constant, 6.626 times 10 to the minus 34 joules seconds, and that'll give you the frequency. If you have frequency, then you can use wavelength equals speed of light divided by frequency. Speed of light 2.998 times 10 to the 8th meters per second. But you could have also used E equals hc over lambda. And that would let you avoid the frequency, and honestly, either way is fine. So if you do this, then h, Planck's constant, divided by time speed of light, and you divide that, or both of those in the bottom and energy per photon on the top, that's going to give you a wavelength, but it's the wavelength in meters. So this number right here is a number I happen to know. That's the energy, that's the wavelength of this light in meters. Finally, 10 to the minus 9 meters per nanometer, or 10 to the positive 9 nanometers per meter, will allow you to get the actual wavelength in nanometers, 656.3 nanometers. So the 3.027, 10 to the minus 19th, that's the joules per photon number. So when you divide by Avogadro's and multiply by 1,000, that's going to give you this number, and that's literally the energy of individual pieces. Then what I did is I didn't use frequency at all. I just went straight for wavelength, which is fine. Wavelength equals hc over that energy per photon. Planck's constant, speed of light, energy per photon. That gets you the meters wavelength, but most of the time these are listed in nanometers. So divide by 10 to the minus 9 or multiply by 10 to the positive 9, 656.3 is the answer. So a lot of mathematical dexterity, all right? Your calculator is going to be your good friend here, definitely. But it is all stuff you can do. Any questions on this process? In lab, there was a conversion that we used that went straight from kilojoules per mole to wavelength in nanometers. That's not a conversion that I use a lot in my day-to-day world, but on the other hand, if you wanted to put that on your note sheet, that would be fair game. So in that case, it was a 1 times 10 to the 5th number. I don't remember exactly, but you could divide that by this to get the wavelength in nanometers direct, which is totally cool. Your call. Questions? Now, here is another kind of question you're going to see. Now, everything we've done so far has been electromagnetic radiation, visible light, ultraviolet, gamma rays, radio waves, stuff like that. But particles, when they're small enough, will have a wavelength associated with them as well. Now, you know that this is a particle problem because you're seeing grams or kilograms, all right? And things with mass, grams or kilograms, will not be photons, because photons are light. Supposedly photons have no mass. Another thing about mass things is that they don't travel at the speed of light, and this goes back to Einstein's relativity. So you won't see speeds of light listed for problems. You might see like 75% the speed of light or something, but you won't see the actual speed of light. So this is a question about wavelength, but it's wavelength for a particle. And when you have particles, you need to use the de Broglie wavelength equation. So see if you can use all this information to figure out what the wavelength of the electron is going to be. One big caveat here is you do need to put masses in kilograms on these kind of problems. And so it's often that you'll see a mass in grams. Make sure you turn it into kilograms. See if you can figure out which of those will be the right answer. So one thing about quantum stuff that's really weird is that light can behave like a particle, and that's what one time I was lecturing, and this person's phone went off, and in my mind, I'm a stupid jerk. It was my own phone. So anyway, oh yeah, it's okay. Prophet back on. Okay, so one thing that's really weird about quantum, man, is that light can behave like a particle. That's Einstein's photoelectric effect. Light goes on to the metal detector, starts to activate and stuff. Whoa, all right, because why would light be like a particle, all right? This is the other weird part, because particles can behave as waves, and it only applies to really small particles, all right? So that's why de Broglie wavelength is kind of a weird thing, but it's really important, because that's what allowed then electrons as waves to build into 1s2, 2s2, and all that kind of jazz. So this is the de Broglie wave equation. It is a wavelength. It looks kind of like the other ones, but it is different. It's the wavelength of a particle, and you know that because particles have mass m. All right, it'll be a mass in kilograms to make the units work out, and the speed won't be the speed of light because officially particles aren't supposed to travel at the speed of light. So h over mv is what you want to do. Now h 6.626 times 10 to the minus 34 joules seconds. Mass in kilograms, take this number and divide by 1,000. So it would be 9.109 times 10 to the minus 31. You can use the speed as is, but initially the wavelength that comes out will be in meters, all right? And so the wavelength in meters doesn't make any sense based on the values up here. However, if you go on then and turn meters into nanometers, because nanometers is a huge part of this, you will get answer D, all right? So initially the wavelength, 6.06 times 10 to the minus 12, that's a unit of meters. And if you convert that into nanometers, you will get the 10 to the minus 3 value right there. So a little bit of a sneaky part right there, but just more calculator dexterity. Any questions? We've got time to do one more question. This is now beginning to get into the quantum numbers. And when you do all the calculus, which is Math 254 math, on these crazy wave functions, you get out NL, M sub L, and M sub S. And with those 4 quantum numbers, you can describe all the electrons and atoms, stuff like that. But you have to know which quantum numbers are allowed and which ones are not allowed. So one of the sets up there of quantum numbers is a disallowed set of quantum numbers. And see if you can figure out which one it is and think about why it is. Excellent. Okay, 4 quantum numbers. N, principal quantum number, shell quantum number, whatever, always starts at 0, goes up to infinity. But it's never negative, it's never 0, never fraction, stuff like that. L depends on N. It always starts at 0, goes in whole numbers up to n minus 1. And M sub L, which is listed there, has a dependence on L. M sub L goes from minus L to 0 to plus L. Now, even though this problem doesn't talk about it, M sub S, which is the 4th quantum number, plus or minus 1/2. Those are the only values, and it doesn't depend on anything else. So if you look at N4, 6, 2, 3, 1, those are all positive whole numbers, so the N's are okay. Now, if L is 1 when N is 4, that's okay, because N of 4 means you could have L values of 0, 1, 2, and 3. You always go up to N minus 1. And M sub L minus 1 is cool when L equals 1, because M sub L goes from minus L to plus L. That would be minus 1 to plus 1, minus 1, 0, plus 1. So this is a legit set of quantum numbers, no problem. N equals 6, cool. L can't be any bigger than N minus 1, so 5 is okay. M sub L minus 5 to positive 5 in whole numbers. 0 is certainly one of them, so that's okay. But what's wrong when N is 2 and L is 2? What's going on there? L has to be no bigger than n-1. Yeah, exactly. So C is the trouble child here. You can't have n and L be the same. L has to be less than n. All right. So yeah, right away, and I think everybody figured that out pretty well. The rest of these are all legit sets. Remember that if you see L of 0 or M sub L of 0, those are actual values. It doesn't mean they don't exist. All right. So this would be a legit set of quantum numbers. L of 0 is okay when n equals 1, and M sub L equals 0 is a legit value of M sub L when L equals 0. Questions on that? Okay. At this point, I want to stop this, and Jose, for very good reasons, was not at class presentations. You can probably see why. And I'm glad to see you again, Jose. Jose is going to present. He's going to present back there because he's definitely dealing with some issues still. So if you don't mind, we'll all turn around and look at him here. Jose and all the rest of you, thank you for doing this. Whenever you're ready to take the stage, you can just sit right there if that's easy. Yeah.
All right, so my name is Jose. I will be presenting about lead. So lead plays a significant role in human society. The earliest use of lead is around 6,500 BC. That's in modern day Turkey. It was found in a sculpture. It's also said that Egyptians around 3,000 or 4,000 BC used lead to glaze their pottery. The Roman Empire revolutionized the way of the uses of lead. They used it in various things. At the peak of the Roman Empire, they would mine up to 80,000 tons of lead annually, something only accomplished after the Industrial Revolution. They would use it to cook utensils, such as pots and pans, also in cosmetics. And it's even said that the higher class would use lead as a sweetener. They would concentrate grapes in pots made out of lead, and the acetate and lead ions would combine it to be like a lead sweetener. They would also use it in combat, such as projectiles. The more sinister use was them using it they would melt the lead and throw it onto their opponents in combat. It's even said that the the coin of the Roman Empire was 30% lead. And some people even speculated that lead consumption was a possible reason why the Roman Empire fell, but other reasons were found to be more reasonable to why they fell. So lead, the symbol for lead is Pb. It's the 82nd element on the periodic table. Its molar mass is 207.2 grams per mole. It's very versatile. It's very abundant, flexible, and can form alloys with copper, making it stronger. Its density is 11.35 grams per centimeter cube, so it's classified as heavy metal. It's got around 13 isotopes, and pure lead is a bluish white color. So the main way of obtaining lead is through open cast mining. The ore is obtained, it is then taken to a processing plant where it is crushed into smaller pieces. From there on, it's concentrated, and then it is melted into ingots for transportation and industrial use. A big use in lead is the lead acid battery. That was invented in 1859 by French physicist Gaston Planté. It's the first rechargeable battery introduced to the world. Despite having a low energy density, it could deliver high currents, which means it could deliver bursts of powers when it is required. That makes it very useful in the automotive and also the industrial starter battery industry. It's very affordable, which makes it accessible to various applications. The key component in the rechargeable battery is converting lead into lead sulfate when it discharges, and the opposite when it recharges. So during recharge, the lead sulfate turns back to pure lead. It's also used in the plumbing system, or was used at least. So it would be used for clean water supply and also just for sewage. Its malleability, durability, and corrosion resistance made it very popular for pipes. However, this was before lead poisoning became a big thing, which has made it less predominant.
Oh, forever. Third one this morning. Sorry about that, Jose. So keep going.
Which has made it less predominant, and more alternative methods are being used now for pipes, for sewage and anything fire related. It's also found in various other products such as radiation shielding, medical imaging, and also nuclear facilities. So anything that needs protection from radiation, lead is a good element to have in the protection. It's also used in electronics for joining circuits together, and it's also used in bullets, weights, paint, due to its thickness, density, and opacity. It's also said that it accelerates the drying time of paint. Lead paint was a big thing in America and Europe during the 19th century at its peak use. The lead paint was said to contain around 70% lead, which is a large amount. That was before it got banned in 1978 from the United States because of lead poisoning. So yeah, lead poisoning is a very big thing with lead. It starts by swallowing or inhaling a substance with lead. So that could be a very long process if you inhale or absorb lead during a long period of time, or it could be something very fast if you were to absorb the lead, well, large amount of lead during a short period of time. Lead poisoning happens. When that happens, the lead goes into the blood, then goes to the organs, then it could go to the tissues or bones. Lead poisoning is a very big thing in industrialized and developing countries due to its low restrictions on the lead industry. There's been moves to try to combat lead poisoning, such as the ban in 1978 of lead paint and also in 1996 of lead in gasoline. Despite all the conjoined efforts to stop lead poisoning, there's said to be around 450,000 children with some lead on their blood, which is not a good thing. So children are very at risk with lead poisoning since they're growing. It's said to stunt growth, lower the IQ, and cause behavioral problems. Lead poisoning occurs through water, through paint, or it could just be through any contamination of just substances with lead. To anyone else, lead poisoning causes lack of energy, lack of appetite, and damages the central nervous system, which in itself causes a lot of more problems. So despite lead poisoning being a big thing, it's said that the lead industry has increased by 26% in the United States from 2001 to 2017, and it has increased 75% worldwide during 2001 from 2001 to 2017. So yeah, the lead industry has usually just gone abroad to countries with less strict rules on the lead industry. And many people compare it to the tobacco industry due to it like downplaying all the health effects it has on the human body. So despite lead causing lead poisoning, we cannot downplay all the big roles it's had on our society, and hopefully in the future, lead could continue to have positive effects on the human society. Thank you.
Nice job. Any quick questions for him? Yeah.
Should we be concerned about using pencils at all?
Oh, sorry, lead isn't in a pencil lead. It's just called lead.
Oh, it's just,
That's a fact.
Pencil lead is graphite like carbon. So
Yeah, it's not even, I don't know.
It did used to be lead though, right? Which is why we still call it that.
yeah.
well, then they made like ultraviolet and whatnot.
Technically, we're writing with diamonds. Different types of diamonds.
Thank you, Jose. Nice job, man. All right, thank you for being here. Friday, we'll finish our review. Have a great day.